Numericals from statistical mechanics. Okay, so I had a question. First question is, which of the following statistical, which of the following cannot exhibit cannot exhibit Bose-Einstein distribution? Which of the following cannot exhibit Bose-Einstein distribution? Okay. Option A, H11. Option B, He24. Option C, sodium 1123. Option D, potassium 1940. Which of the following cannot exhibit Bose-Einstein distribution? Okay, let's try this question. See, Bose-Einstein distribution, it will have particles like what? It will have bosons with it, right? The particles participating in Bose-Einstein distribution are usually bosons. Bosons means what? What are bosons? Bosons are spin integral particles. Even spin integral. Okay, even integral. Spin even integral or whatever. Spin is even integral. Like 1, 2, 3, like that. Okay, not rational. Not like 1 by 2 or 3 by 2. Those are for fermions. Bosons are even integral. Okay, so here if you see in hydrogen, in hydrogen there is one proton and one electron, right? So one proton, one electron. Hmm. So like total spin will be what? Half, half, half plus half, right? Total spin will be one. So even integral, right? Like, that means integral value. That means it's spin. Like that means it's a boson. Okay, that means it's a boson. Helium 24. Helium 24. So two protons. Hmm. Also two neutrons. All right. Yeah. So this one will be what? If you see two neutrons and two electrons also. Yeah. So this one will be your also even integral, because if you see this is 2 by 2, 2 by 2, 2 by 2. So this is giving me 3. The spin is 3. Spin is 3 means this is a boson. Okay. Now even integral doesn't mean even this number even. No, no. Even integral means 2. It would have come, see. What is it? 6 by 2. So even integral. If it had come 1 by 2, this is odd integral. Okay. Next is a what? Sodium 2311. 11 protons, 12 neutrons, 11 electrons. Right? 12 neutrons, 23 minus 11 is 12. So this is 23 plus 11, that is 34. 34 again, like it's giving me what? What is it? If you see, this is what? 11 by 2, 12 by 2 plus 11 by 2. So if you see, this is 34 by 2, that is 17. Yeah, 34 by 2, so 17. 17 is also, this one is also boson. Alright, that is 34 by 2 boson. Now, potassium 40, 19. This will be what? 19 protons, 21 neutrons, 19 electrons. 19 by 2 plus 21 by 2 plus 19 by 2. That will give me what? If you see, this one is 59 by 2. This is your odd integral. Okay, because this is non-divisible. It cannot be divided by 2. This is your odd integral. Odd integral means what? This is a fermion. This is not a boson. Okay, this is not a boson. This is not a boson. Is that alright? So the following cannot exhibit Bose-Einstein distribution. This one. This one is a boson, this one is a boson, this one is a boson, but this is not. Okay. Yeah. Next question. Right, on probability distribution, function of variable x in the range minus infinity to plus infinity is p of x is equal to 10 e to the power minus 2x square minus 4x minus 6. Okay. Maximum probability will correspond to maximum probability will correspond to dash. Probability distribution function of variable x in the range minus infinity to plus infinity is px is equal to 10 e to the power minus 2x square plus minus 4x minus 6. So maximum probability will correspond to dash. That's the question. Okay. Simple thing. Probability is given. So maximum probability, that means what? We have to just take the derivative of probability and equate it to 0. Right? So dpx by dx is equal to 0. So d by dx of 10 e to the power minus 2x square minus 4x minus 6 is equal to 0. That will give me 10 comes out. Divided this one is minus of 4x minus 4 e to the power minus 2x square minus 4x minus 6 is equal to 0. So that will be minus 10, 4x plus 4 e to the power minus 2x square plus 4x minus 6 is equal to 0. This cannot be 0, so this will go to this side. So 4x plus 4 is equal to 0. Yeah, sorry, there's a minus inside. So 4x is equal to what? 4. So x is equal to 1. This is the value x for which probability is what? Maximum. Okay. Question number 3. Consider a system of consider a system of three fermions. Consider a system of three fermions which can occupy which can occupy any of the four available energy states with equal probability. With equal probability. The entropy of the system is the entropy of the system is consider a system of three fermions which can occupy any of the four available energy states with equal probability. The entropy of the system is three fermions are there which can occupy any of the four available energy states. Okay, there are four available energy states. It's three fermions which will equal probability the entropy of the system. Okay, so how can we see four available energy states? One, two, three. Three fermions are there. So how can we see? These are same state fermions like we are not given like up or down anything. So we will just take this as an up or a down. So we'll just consider one kind of thing. So in one state there can be only one fermion which has the upper state, right? We cannot have two fermions like this in the up state. So just one here, like this, like this. This is one. Okay. Next, how can we also arrange it? This one we can leave the gap. This now I can leave the third one and fill the others, right? And also I can leave the first one and fill the others. So these are how many states? One, two, three, four. So four states are there. Okay. So four micro states. These are called what? Micro states. So four micro states are there in which your these are the energy available energy states, and we arrange the three fermions accordingly. Okay, like this. We will left this one, then left this one, left this one, left this one. So there are four micro states. Okay, so entropy we know what? Entropy is S is equal to kV ln omega. Omega is your 4. So it becomes what? kV ln 4. That is 2 kV ln 2 or whatever. This is the answer. Alright. Yeah. Otherwise you can do, or can also do, there are available energy states is 4. Available energy states are, that means this is your G. G is 4. The number of particles is N. Number of particles N is equal to 3. So distribution will be how much? How much? A distribution of number of microstates. Microstates is GCM. So 4C3. This is for what? This is for your fermions. These are fermions, that's why. Okay. So 4 factorial by 3 factorial into 1 factorial. That is 4. S is equal to 2 kV ln 2. Okay. Or ln 4 kV ln 4. Yeah. Okay, next. Question number 3. Question number 4. Considering two consider two different systems. Consider two different systems, each with each with three identical non-interacting particles. Three identical non-interacting particles. Both have both have single particle. Both have single particle with energies E naught, 3 E naught, 5 E naught, where E naught is greater than 0. One system is one system is populated by spin half fermions. One system is populated by spin half fermions, and the other by bosons. The other by bosons. Okay. What's the value of what's the value of what's the value of EF minus EV, where EF and EV are where EF and EV are the ground state energies, the ground state energies energies of the fermionic of the fermionic and boson systems respectively. Boson systems respectively. Okay. What's the value of EF minus EV, where EF and EV are the ground state energy of the fermion and boson systems respectively? Consider two different systems with three identical non-interacting particles. Both have single particle with energies E naught, 3 E naught, and 5 E naught, where E naught is greater than 0. One system is populated by spin-half particle fermion and the other by bosons. What's the value of EF minus EV, where EF and EV are the ground state energies of the fermionic and boson system respectively? Read the question for 2 minutes. So there are two systems. One system is of spin-half fermion, other is one of the bosons. Two systems, and they have three levels: E naught, 3 E naught, 5 E naught. Let's first make two systems. This is for fermion, left side. This is for boson. Okay. What are the energy levels? E naught, 3 E naught, 5 E naught. E naught, 3 E naught, 5 E naught. So these are the systems. Alright. Now, one system is populated by spin half fermions. When you have spin half, that means what is the multiplicity? 2s plus 1, that is 2 into half plus 1, that is 2. Multiplicity 2 means in one state we can have maximum 2 particles, 2 fermions. So, for example, we will just arrange here, right? Yeah, this is one, this is another one. So, this is the arrangement for fermions. Now, 3 particles, right? 3 identical particles. So, here for bosons, see, for boson there is nothing like this. For bosons, we can have in one state we can have all the 3 particles. Okay, that's the thing. So see, fermions, what will be the energy for fermions? See, if this is E naught, so this is your 2 E naught, yeah, 2 E naught, this is your 3 E naught, only one particle. So total particle for fermions EF is equal to 2 E naught plus 3 E naught. This is your 5 E naught. Okay. Now for bosons the total particle, like 3 particles in only E naught, so 3 E naught. So EB is equal to 3 E naught. Okay. So what is the question? Question is, what's the value of EF minus EB? So EF minus EB is equal to 5 E naught minus 3 E naught. That is equal to 2 E naught. Okay, this is your EF minus EB. 5 E naught minus 3 E naught is equal to 2 E naught. That is your EF minus EB. Is that alright? Okay, that is the answer. Okay, so let's move to the next question. That was question number 4. Question number 5. The Bose-Einstein gas has two particles in the in the ith state. whose degeneracy is 3. The number of independent ways number of independent ways of selecting the particles in the state is. The Bose-Einstein gas has two particles in the ith state whose degeneracy is 3. The number of independent ways of selecting the particles in the state is. Okay. So how to solve this question? See, Bose-Einstein gas has particles whose degeneracy is 3. So degeneracy is 3. dg. G is equal to 3. Number of independent ways of selecting the particles in the state. Okay. Then Bose-Einstein gas has two particles in the state. The degeneracy is 3. The number of independent ways of selecting the particle in the state is how much? So this is a Bose-Einstein gas. So Bose-Einstein gas means it's a boson. So for boson, the number of microstates is omega is equal to Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Right? So here Ni is how much? Ni is 2 because there are two particles. So Ni is 2 and Gi is 3. So omega will be 2 plus 3 minus 1 factorial divided by 2 factorial 3 minus 1 factorial. Okay, so 5 minus 1 is 4 factorial divided by 2 factorial into 1 factorial. So that is 24 by 2, that is 12. Okay. I do a mistake. Okay, 3 minus 1 is 2, sorry. 2, this is 6. So number of microstates here is 6. Number of microstates is equal to 6. So your entropy, oh, this one is only asked. Number of independent ways of selecting the particles in the state. So that the answer will be 6. Okay. Next question, question number 6. Question number 6, write down. A fermion has two particles in the ith state whose degeneracy is 3. Find the number of independent ways find the number of independent ways of selecting selecting the particles in the state, selecting the particles in the state, in the state is, like, find the number of independent ways of selecting the particle in the state, right? So this is a fermion. So this is not a boson, this is a fermion. For fermion, the formula is different than the boson. So for fermion, the arrangement would be simply omega is equal to G C M. G is how much? Degeneracy is 3. 3. Number of particles is 2 particles. So 2. So 3C2, that means 3 factorial divided by 2 factorial into 1 factorial. That is 6 by 2. The answer is 3. Okay. So number of microstates will be 3. Yeah. Next question. Question is question number 7. Question number 7. Ground state energy. Ground state energy of four classical particles kept in a kept in an infinite square well potential, infinite square well potential is, ground state energy of four classical particles kept in an infinite square well potential is n square pi square h cut square by 8 ms square. So find m. The question. Ground state energy of four classical particles kept in an infinite square well potential is this much. Find m. Okay. So there are four classical particles in an infinite square well. Okay. So classical particles are distinguishable. Okay. Four classical particles distinguishable. So we just can simply place them A B C D. Okay. There is no problem with it. We can simply place all the particles in the first state. All right. So first state ground state energy is what? Pi square h cut square by 8 ms square. So 2 ms square. Right. It's 2 ms square, isn't it? So this one is four particles here. So for four particles, it will be 4 pi square h cut square by 2 ms square. But the question is n square by 8, right? Answer is n square by 8. So 8 should be in the new denominator. So if I write 8 in the denominator, that means I am multiplying 4 in the denominator. That means I have to multiply 4 in the numerator. Okay. See, 4 by 2 is 2. This is also 16 by 8 is 2. So the numerator becomes what? 16 pi square h cut square by 8 ms square. So your n square is what? N square is your 16. So n is how much? N is a 4. Okay. So the answer is 4. Is it alright? Okay. Next question. Question number 8. Three non-interacting fermions minus E are distributed in the state minus E, 0, E and 2E. Entropy entropy of the system, if total energy is 0, is total energy of the system is 0, is you have to find the entropy here. Three non-interacting fermions are distributed in the states minus E, 0, E, 2E. So entropy of the system, if total energy of the system is 0, total energy of the system should be 0. E total is equal to 0. So how should we arrange this? Four states minus E, 0, E, 2E. We have three fermions. We have three fermions. Alright. So how will you arrange this? So that to E total will be 0. See, if I put one fermion here, another here, another here. So this will be 0, minus E plus 0 plus E, 0. This is 1. But the thing is, we can have only one fermion in one state because these are only like upward up spin, because nothing is mentioned, so we have to take up spin. We cannot, you might ask if we can have something like this 1 in 2E and 2 in minus E, but this is not possible because this is a fermion. Fermions cannot be in the same state in the same level, so this is not possible. So only one arrangement is possible. So omega is your 1. Omega is your 1. Number of microstates is 1. So entropy will be entropy S is equal to K ln omega. K ln 1. So that is 0. Is that alright? Okay. So entropy is 0. Okay. Now exactly I will ask the same question, but for bosons, three non-interacting bosons available available bosons with available energies minus E, 0, E. Okay. So that three non-interacting bosons are distributed among available energies minus E, 0, E, so that total energy is equal to 0. Total energy is equal to 0. So find the entropy of the system. Find the entropy of the system. The non-interacting bosons with available energies minus E, 0, E, so that total energy is 0. Find the entropy of the system. So for bosons we can have as many bosons as possible in one state. So there is no problem. Total energy should be 0. So let's minus E, 0, this is E. So we can have all the three bosons in here, right? All the three bosons here, because total energy is 0 here. Then what can have? Uh, yeah, minus E. This is another state. One here, one here, another here. Why I am doing this? Because this one is bosons are indistinguishable, and like we cannot distinguish them. So we have to give the symbols like this. So there are totally two states. This is one, this is two. So number of microstates is 2. Okay. So entropy will be K ln omega. That is K ln 2. Okay. And the last question, question number 10. What will be the average energy? What will be the average energy per particle for a system in equilibrium at temperature T, consisting of bosons, each of which can occupy energy levels of energies 0 and F2 epsilon. The degeneracy of both the levels of both the levels is 2. Right? What will be the average energy per particle for a system in equilibrium at temperature T, consisting of bosons, each of which can occupy energy levels of 0 and 2 epsilon? The degeneracy of both the levels is 2. Okay. So how will we solve this? See, there are two energy levels, 0 to epsilon. Total, this is your total. Okay. Total energy must be uh, zero. Okay, there is no. We have to find what is the average energy. Okay, so we need total energy in a state and degeneracy also. So there will be how many particles are there? Okay, so see, I can arrange mm, consisting of four. Okay, consisting of four bosons. Okay, these are four bosons there actually. So I can have here two, two here, two here, one here, and one here. The energy will be what? Zero. But degeneracy is how much? 3. Yeah? Is that alright? Okay. Now, uh, for example, I will have one particle here and one particle here. So this is not four bosons, this is two bosons only. Two bosons. So one particle here, one particle here. So this is giving me 2 epsilon, right? Okay. One particle here, one particle here. This is also giving me 2 epsilon. Then suppose one particle here, one particle here, right? So this will be giving me 4 epsilon. And what is another one? One here, one here. And, okay, this cannot be here. Sorry, this state is not possible. This is 4 epsilon. We need 2 epsilon in this state. Okay, this is not possible. This is another one is this. So this is 4. 2 epsilon is your 4. Degeneracy is 4. Next is 4 epsilon. So here, 4 epsilon. Okay. What can be another one? Both of them here, 4 epsilon, or both of them. So degeneracy here is 3. Okay. So this is the like arrangement. We know what is average energy. We need average energy. Average energy is equal to summation Gi Ei e to the power minus beta Ei divided by partition function, right? So Gi first, G1 is what? 3. 3 into 0 into e to the power whatever there is, it doesn't matter because it's 0, plus next state is 4. So 4 plus 4 into uh, 2 epsilon 2 epsilon e to the power minus 2 beta epsilon plus 3 into 4 epsilon e to the power minus 3 beta epsilon is equal to 3 e to the power minus beta into 0 plus 4 e to the power minus 2 beta epsilon plus 3 e to the power minus 3 beta epsilon. So this is 0, this is your 8 epsilon e to the power minus 2 beta epsilon plus 12 epsilon e to the minus 3 beta epsilon whole divided by 3 plus 4 e to the power minus 4 beta epsilon plus 3 into e to the minus 3 beta epsilon. That will be the average potential. Is that alright? Okay. I hope you understood this question. So these are some questions we did from statistical mechanics, and this is a very important question for your JEST exam. So I hope you understood. Okay, we'll be solving more questions in the coming sessions. Thank you.